There are atoms in your body that were born in the first minutes of the universe. This audiobook invites you on a 2-hour journey to that remote origin when from a sea of pure energy emerged the first elements. Hydrogen, helium, and lithium. Every star, every planet, every breath we take has its roots in that primordial moment. We will discover how from that cosmic alchemy was born the matter that today forms mountains, oceans, and also us. Imagine for a moment that the universe is a giant puzzle. Each piece, each element plays a crucial role in the whole. However, where do those pieces come from? The answer lies in the dawn of time. At the moment when everything began, in an event known as the Big Bang. This monumental event not only marked the beginning of space and time, but also sowed the seed for the creation of the first light elements. Let's talk about the Big Bang. An explosion of energy and matter that occurred about 13,800,000,000 years ago. In an instant, the universe went from being an infinitesimal point to expanding at a dizzying speed. But what does this mean for the formation of elements? In the early moments of existence, the universe was an extremely hot and dense place where conditions were perfect for the creation of the first atomic nuclei to begin. Primordial nucleosynthesis is the term we use to describe this process. In a brief span, less than 5 minutes after the Big Bang, the first nuclei of hydrogen, helium, and lithium began to form. This may seem complicated, but imagine you are cooking a soup. Instead of individual ingredients, the atoms were mixing to create the foundations of what would eventually be all the elements of the universe. The temperature and density of the universe at that time were crucial. Only in such an extreme environment could these nuclei be born. As the universe continued to expand and cool, hydrogen became the most abundant element, representing almost 75% of all matter. Why is hydrogen so important? This element is not only the simplest, but also acts as the building block for all other elements. Think of hydrogen as the basic brick in building a house. Without it, you couldn't erect the walls or the roof. Helium, which accounts for about 25% of matter, was formed in this same process. As hydrogen grouped and reacted, helium emerged as a natural product of these interactions. But have you ever wondered why helium is less abundant than hydrogen? The answer lies in the dynamics of how nuclei are formed, a process that is both fascinating and complex. On the other hand, lithium is an element that, despite being the third lightest element, is remarkably scarce compared to hydrogen and helium. This raises an intriguing question. How can such a light element be so rare? The formation of lithium is due to processes that are a bit more complicated and less efficient than the production of hydrogen and helium. In a sense, lithium is like that hidden treasure that we all want to find but is not so readily available. As we delve deeper, we encounter stars, which play a vital role in stellar nucleosynthesis. In the hearts of stars, hydrogen fuses to form helium through nuclear fusion, a process that not only generates new elements but also releases an immense amount of energy. These stars are true cosmic factories, where light elements are transformed and enriched throughout their life cycle. However, the journey of light elements does not end there. When the largest stars reach the end of their lives, they explode in spectacular supernovae, scattering the light elements they have created throughout their existence. This explosion not only lights up the night sky, but also contributes to the abundance of these elements in the universe, fueling the next generation of stars and planets. Dark matter, that enigmatic component of the universe that we cannot see, also plays a crucial role in the formation of light elements. Although it does not interact with light, its gravitational influence helps group hydrogen and helium into clouds that eventually become stars and galaxies. Without dark matter, the universe could be a very different place. Gravity, of course, is the thread that ties everything together. It is the force that attracts hydrogen and helium, allowing them to group and form more complex structures. Without this fundamental force, light elements would not have the opportunity to come together and give rise to the stars and galaxies we see today. In our own solar system, light elements play a fundamental role in its formation. As the solar system was forming, These elements were distributed in such a way that gave rise to planets, moons, and other celestial bodies. The chemistry of water, which is made up of hydrogen and oxygen, is a perfect example of how these light elements are essential for life as we know it. The fusion energy generated by stars, coming from the fusion of light elements, is what keeps stars shining for billions of years. This energy is one of the most powerful forces in the universe, and understanding it leads us to reflect on the evolution of stars and their role in creating new elements. Finally, the story of light elements is not only linked to the formation and evolution of our universe, but also has profound implications for the search for life on other planets. Understanding how these elements formed can help us discover what conditions are necessary for life to flourish in distant places. As we close this first chapter of our journey, it is clear that light elements are much more than simple atoms. They are the foundations of everything we know, and their history is intertwined with that of the universe itself. Have you ever felt so small when looking at the stars? The truth is that each of us is made up of these same elements, the same ones forged in the hearts of stars and that have traveled through time to become part of us. What really happened in that initial moment when everything we know began to exist? Let's talk about the Big Bang, an event so monumental that it not only gave rise to the universe but also laid the groundwork for the creation of the lightest elements we find today. This event was not an ordinary explosion. It was an explosion of energy and matter that expanded at an unimaginable speed, marking the beginning of time and space as we know them. Have you ever wondered how the first atoms were formed? In the moments immediately following the Big Bang, the universe was an extremely hot and dense place, akin to a thick soup of fundamental particles. In that whirlwind of energy, the first atomic nuclei formed, a process known as primordial nucleosynthesis. During this phase, conditions were perfect for protons and neutrons to come together, resulting in the first nuclei of hydrogen, helium, and to a lesser extent, lithium. But why only these elements? Imagine you are in a kitchen trying to make a recipe with limited ingredients. That's how the universe acted in its early moments. It only had a restricted number of particles to work with. The temperature was so high that any attempt to form heavier elements was impossible. In that context, hydrogen became king, as it was the most abundant ingredient in this primordial soup. But what made hydrogen so prevalent? As the universe continued to expand, the temperature began to drop. It was during this cooling era that hydrogen nuclei managed to capture electrons, forming complete atoms. This was a crucial step because it allowed hydrogen, along with helium, to start clumping together and forming the first stars. As the universe cooled and expanded, a balance began to be established between gravity and radiation pressure. But what role does gravity play in all this? Gravity, that force we often take for granted, became essential for gathering hydrogen and helium. Just as a vacuum cleaner picks up dust from a room, gravity began to attract these particles. Over time, these gas clumps densified and collapsed, giving rise to the first stars. These stars in turn became factories of elements. But first, let's talk about how helium was formed. Helium, the second lightest element, was formed in significant amounts during primordial nucleosynthesis. When hydrogen nuclei fused in a hot and dense environment, they began to create helium. This process is like having two Lego pieces that, when put together, form a new figure. However, helium is not just a product of fusion, it is also a witness to the history of the universe. Its presence in the cosmos tells us a lot about how and when stars formed. Now let's talk about lithium, the rarest element among these three. While hydrogen and helium are abundant, lithium is like that last piece of pizza that always remains in the box, much appreciated but hard to find. It formed in a similar way but in much smaller quantities. Despite its scarcity, lithium plays an important role in the chemistry of the universe and helps us understand its evolution. Over time, stars, composed mainly of hydrogen and helium, began to live and die in cycles, contributing to the creation of more light elements. But how does this magic happen inside a star? The answer lies in nuclear fusion. As stars compress under their own gravity, the temperature in their core increases, allowing hydrogen nuclei to fuse to form helium. This process releases an immense amount of energy, which we see as starlight. Supernovae, giant explosions of dying stars, also play a crucial role in this. When a star explodes at the end of its life, it disperses light and heavy elements into space, enriching the intergalactic medium. It's as if a star in its twilight shares its treasures with the universe, planting the seeds for new stars and planets. But how does this affect the abundance of light elements? Dark matter, that enigmatic substance that makes up a large part of the universe, also has its story in the formation of light elements. Although it does not interact with matter in the same way, its gravitational influence helps shape the structures of the cosmos. Without dark matter, the universe could have been a very different place, affecting star formation and consequently element production, as we explore the relationship between gravity and the formation of elements. It is fascinating to see how this force not only helps gather hydrogen and helium but also shapes galaxies. These massive structures are home to billions of stars, each contributing to the life and death cycle that generates new elements. But what happens to these light elements in our own solar system? Light elements were distributed throughout the solar system during its formation, influencing the composition of planets, moons, and other celestial bodies. The chemistry of water, for example, reflects the abundance of hydrogen and oxygen, two elements that are fundamental to life as we know it. Without them, Earth would be a very different place, likely devoid of life. In conclusion, the importance of the Big Bang and the subsequent primordial nucleosynthesis is fundamental to understanding how light elements formed in the universe. From hydrogen and helium to lithium, they all have a rich and intertwined history that helps us understand not only our origin but also the universe itself. At the end of the day, every time we look up at the starry sky, we remember that we are part of this vast cosmic story. If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey. Primordial nucleosynthesis is a fascinating concept that takes us to the early moments of the universe where the magic of creating light elements took place. Did you know that just a few minutes after the Big Bang, the universe was a completely different place? At that moment, everything was heat and energy, and elementary particles began to group together to form what we now know as the first atomic nuclei. But how did this happen? The story begins in an extremely hot and dense environment where protons and neutrons, the basic components of the atomic nucleus, started to come together. Imagine you are at a lively party where the music is blasting and the energy is contagious. In this dynamic environment, particles collide with each other and some manage to form pairs. Thus, protons group with neutrons, leading to the formation of the first nuclei of hydrogen, helium, and lithium. An interesting fact is that during those first minutes, approximately 1/4 of the helium that exists in the current universe was formed. This is astonishing, considering that helium is a crucial element for many nuclear reactions that occur within stars. But why were only these light elements formed and not heavier ones? The answer lies in the extreme temperature and density of the primordial universe. As the universe began to expand, its temperature started to decrease. It's like being in a pot of boiling water that gradually cools down. As the heat diminishes, particles have less energy to overcome the repulsion between them and join together. This means that only the lightest elements, such as hydrogen, helium, and lithium, could form during those early moments. Later on, when stars began to form, heavier elements were created, but that is a story for another time. It is fascinating to think that everything we see around us, including ourselves, comes from this process of primordial nucleosynthesis. The hydrogen atoms that make up most of our matter were created in those early instants, and helium, which is the second most abundant element in the universe, also originated from this event. But what about lithium? This element, although less abundant, formed in a similar way but in much smaller quantities. Now imagine that the universe is like a huge factory of elements. In this factory, protons and neutrons are the machinery parts, and primordial nucleosynthesis is the assembly process. However, this factory could only produce a certain amount of products, and that production was limited by the conditions of the environment. Thus, in those crucial moments, only a few light elements were created before the universe expanded and cooled. Some might wonder, why is it so important to understand primordial nucleosynthesis? The answer is simple. It helps us understand where we come from. By studying how these first nuclei formed, scientists can unravel the history of the universe. It allows us to connect the dots between the matter that makes up stars, planets, and ultimately life itself. As the universe continued to expand, it also became more complex. The formation of the first stars and galaxies allowed light elements to combine and give rise to heavier elements through nuclear processes inside stars. But it all began with those first moments of primordial nucleosynthesis, where the basic ingredients of the universe began to take shape. Human curiosity drives us to understand these origins. We wonder, what else happened in those early moments? The answers lie in current research, where scientists analyze cosmic background radiation and other phenomena to shed light on the state of the universe in its infancy. Each discovery brings us one step closer to unraveling the mysteries surrounding our existence. Finally, it is essential to remember that although the light elements formed in primordial nucleosynthesis are just a small part of the vast universe, their impact is enormous. Without them, stars, planets, and of course life as we know it would not exist. So the next time you look at the starry sky, remember that those tiny nuclei of hydrogen and helium have a story that dates back to the very origins of the cosmos. A story of creation, transformation, and above all, connection. The era of radiation was a crucial period in the history of the universe, a time when everything we know was in a primitive, hot, and energy-filled state. Have you ever imagined what that young and tumultuous universe was like? At this stage, the temperature was so high that particles could barely hold together. In this vast ocean of energy, photons moved at an impressive speed. But what did this mean for the formation of light elements? Photons, those particles of light that filled space, had the power to break the connections between subatomic particles. This caused a kind of chaos where protons and electrons were constantly interacting but unable to form stable atoms. For light elements to emerge, it was necessary for the universe to cool down a bit. How does this cooling happen in such a hot place? As the universe expanded, it began to lose temperature. This process of expansion is similar to when we inflate a balloon. The more air we add, the bigger it gets, and as it expands, the temperature inside decreases. In the universe, that expansion allowed protons and neutrons to come together to form nuclei. But what happened to the electrons? With the cooling, electrons began to join those newly formed nuclei. Imagine that protons and neutrons are a group of friends at a festival. When it's very hot, they can't get close to each other, but as the temperature drops, they feel more comfortable and start to form small groups. This is how the first atoms of hydrogen, helium, and lithium were born. But why these elements and not others? The main reason is the simplicity of these nuclei. Hydrogen, made up of a single proton, formed in large quantities. Helium, which has 2 protons and 2 neutrons, was also created abundantly, but in smaller proportions. Lithium, with 3 protons, was a bit scarcer. This process of nucleus formation in the primitive universe is known as primordial nucleosynthesis. But why is it so important to understand? These light elements are the building blocks of everything we see around us. Without them, we wouldn't have stars, planets, or life itself. Imagine you are building a house. You need bricks, cement, and other basic materials to start. In the case of the universe, hydrogen and helium are those essential materials. Without primordial nucleosynthesis, we wouldn't have the foundations upon which everything was built. However, the era of radiation did not last forever. Over time, the universe continued to cool and expand. the density of matter began to decrease, allowing the first atoms to cluster and form clouds of gas. But what would happen next with those atoms? The answer lies in the power of gravity, which would play a fundamental role in the formation of stars and galaxies. As the clouds collapsed under the influence of gravity, the temperatures inside increased, creating ideal conditions for nuclear fusion. This process is key to understanding how light elements not only began to exist, but also how they transformed into heavier elements over time. But that's a topic for another part of our story. For now, it is fascinating to consider that from an expanding and energy-filled universe, the first elements emerged that would eventually give rise to everything we know. The era of radiation teaches us that although everything seemed chaotic at the beginning, there was an underlying order that would allow for the creation of matter. Without that first stage, our universe would be a very different place. And perhaps we wouldn't exist to tell the tale. So the next time you look at the starry sky, remember that those bright lights are made up of the same elements that emerged billions of years ago in a universe that was just beginning to find its shape. The story of light elements is in essence the story of our own origin. Hydrogen, the simplest and most abundant element in the universe, is the true protagonist of our cosmic story. But what makes it so special? To understand this, it is important to think of hydrogen as the fundamental building block of everything we know. Just as a house is built with bricks, the universe is primarily composed of hydrogen. In fact, it is estimated that approximately 75% of the visible matter in the universe is hydrogen. It is incredible to think that most stars, including our neighbors in the Milky Way, are largely made up of this element. But why is hydrogen so abundant compared to other elements? The answer lies in its simplicity. Hydrogen consists of a single proton and a single electron, making it light and easy to form. In the context of the Big Bang, when the universe was still a hot and dense soup, the first hydrogen nuclei began to form rapidly. Thus, in a cosmic blink of an eye, hydrogen emerged as the first element. Imagine a vast ocean of possibilities where each wave represents a new opportunity to form something. In this primordial ocean, hydrogen not only floated but also interacted with other nuclei to create helium and other light elements. But what about helium? It is the second most abundant element in the universe, but it could not exist without the presence of hydrogen. Helium is like hydrogen's inseparable companion in the cosmic dance. The importance of hydrogen goes beyond being the most abundant element. Its role is fundamental in nuclear fusion, the process that powers stars and allows them to shine. In the hearts of stars, hydrogen fuses to form helium, releasing a tremendous amount of energy in the process. This phenomenon is the engine that fuels the light and heat of stars, including our own sun. Without hydrogen, we would have no stars, and without stars, we would have no life as we know it. Now, what about the creation of other elements? Through nuclear fusion, hydrogen not only gives rise to helium, but also acts as a base for the formation of heavier elements in later cycles. As stars age and exhaust their supply of hydrogen, they begin to fuse helium and other elements, creating a variety of new nuclei. Thus, hydrogen is the first step in a long journey that leads to the creation of a rich and diverse periodic table. But what happens when a star reaches the end of its life? This is where hydrogen plays another crucial role. In supernova explosions, when stars die, they release a large amount of elements into space, enriching the interstellar medium. This new material, which includes elements that have formed from hydrogen, becomes the raw material for new stars and planets. Thus, hydrogen is not just an element in itself, but a transformative agent that perpetuates the cycle of stellar life. The relationship between hydrogen and gravity is also fascinating. Gravity, that force that holds everything together, helps to group hydrogen to form dense clouds that eventually collapse to give rise to new stars. Without hydrogen, gravitational forces would not have the necessary material to form these structures. It is as if hydrogen were the essential ingredient in a cosmic recipe where gravity is the chef that mixes everything to create something new. If we look at our own solar system, hydrogen and helium are the main components of gas giants like Jupiter and Saturn. These planets act as large cosmic laboratories where hydrogen manifests in surprising ways. Additionally, hydrogen is a key component of the chemistry of water, a vital element for life as we know it. Without it, the existence of water on our planet would be impossible, highlighting the importance of hydrogen in life itself. But how does hydrogen relate to the search for life on other planets? The presence of hydrogen and water is a crucial indicator in the search for habitable environments. If we find hydrogen on other worlds, it could mean that there is water and therefore potentially life. Research on the abundance of hydrogen in the universe offers us clues about where to search for life in the cosmos. In summary, hydrogen is not just a chemical element. It is the core of the universe's story, from its role in the creation of stars to its influence on the formation of planets and life. Hydrogen is the thread that connects our existence to the vast cosmos. By understanding its importance, we can begin to glimpse the enormous role this element plays in the grand scheme of the universe. In every corner of the cosmos, hydrogen reminds us that we are part of an interconnected web of matter and energy, where everything has a place and a function. In the vast universe, there is one element that stands out for its importance: helium. But how did this colorless and odorless gas, despite its simplicity, have a monumental impact on the structure of the cosmos? The story of helium begins just after the Big Bang, at a time when the universe was a hot soup of subatomic particles, where hydrogen and helium were destined to be born. To understand the creation of helium, it is crucial to remember that in the early moments of the universe, everything was extremely dense and hot. In this chaotic environment, protons and neutrons began to come together. But why is helium so special? The answer lies in its relationship with hydrogen, the most abundant element in the universe. In a sense, we could say that hydrogen is the building block, while helium is the result of the first great transformation. When hydrogen protons joined to form helium nuclei, they did so through a fascinating process called nuclear fusion. This phenomenon not only produces helium but also releases enormous amounts of energy. Imagine this. At the heart of a star, hydrogen nuclei collide and fuse, creating helium and releasing light and heat. This is how helium becomes a byproduct of a reaction that is, in essence, the engine of the universe. Now, although helium accounts for about a quarter of the mass of the visible universe, its formation was not a simple process. Think of an art workshop where, instead of painting with colors, the artists are creating elements from subatomic particles. In this workshop, protons act as the brush and neutrons as the color palette, and together they begin to create helium in a process that requires precision and the right conditions. A key moment in the history of helium is primordial nucleosynthesis. During the first minutes after the Big Bang, the universe expanded and cooled enough to allow hydrogen nuclei to combine and form helium. This process was fleeting, a brief moment in cosmic history, but its impact was lasting. Without that moment, helium would not exist in the quantities we know today. The scarcity of helium compared to hydrogen is astonishing. While hydrogen is almost ubiquitous, helium is a rare treasure. Why does this happen? The answer lies in how these elements are produced. Most of the hydrogen that exists in the universe has remained unchanged since its formation, while helium is primarily produced in stars. Thus, helium becomes a product of stellar life cycles, where it is created, consumed, and eventually dispersed into space. As stars evolve, helium accumulates in their cores. When a star exhausts its supply of hydrogen, it begins to fuse helium into heavier elements. This process is similar to an assembly line in a factory, where helium is transformed into other elements, enriching the universe with new materials. But here is where it gets even more fascinating. When these stars explode in supernovae, they launch helium and other elements into space, seeding the cosmos with the ingredients necessary for the formation of new stellar systems. Helium's connection to life on Earth is equally intriguing. Although it cannot be used by organisms as a source of energy, its presence in the atmosphere and its role in the universe show us how every element, no matter how simple, has a place in the grand cosmic puzzle. What would happen if we didn't have helium? Without this element, stars would not shine as they do, and the universe would be a very different place. For those curious about the search for helium in the cosmos, there are innovative methods that scientists use to detect it, from telescopes that observe the light emitted by stars to probes that analyze the composition of distant planets. Astronomers are in constant pursuit of this elusive element. Each discovery about helium not only helps us better understand our own solar system, but also offers clues about the formation of other systems in the universe. The story of helium is a lesson about the interconnectedness of all elements in the universe. Each helium atom that forms is the result of a cosmic journey that began with the explosion of the Big Bang and continued through the life and death of stars. This endless cycle of creation and destruction is what makes helium more than just a simple gas. It is a symbol of the dynamism of the universe. In the end, helium reminds us that, although it may seem like a simple element, its story is profoundly complex and fascinating. It invites us to look up at the stars and to wonder about our place in the vast cosmos. What other secrets do the light elements surrounding us hold? The answer to that question may be the key to understanding not only the universe, but also our own origin and destiny. What makes lithium such a special element in the vast universe? While hydrogen and helium are abundant, lithium seems to be a rare treasure, like a hidden gem in an ocean of gas. To understand its formation, it is essential to look back to the past, specifically to the moments following the Big Bang, when the universe was an extremely hot and dense place. In those early minutes, primordial nucleosynthesis took place. Here, the first nuclei of hydrogen and helium were formed, but lithium, had a different fate. So why is this element so scarce compared to its lighter siblings? The answer lies in how it was created. Although it formed in small amounts during the Big Bang, most of the lithium we know today has been destroyed in nuclear reactions within stars. To illustrate this, imagine a cake you are baking. If hydrogen is the flour and helium the sugar, lithium is like the cherry on top, something added in small quantities but offering a unique flavor. During primordial nucleosynthesis, about 3 helium atoms were formed for every lithium atom. Isn't it amazing to think about how this small number has influenced the chemistry of the universe? Now let's talk about the peculiarity of lithium. This element has a couple of stable isotopes which are like different versions of a song that share the same melody but have different styles. One of those isotopes is lithium-6, while the other is lithium-7. Did you know that these isotopes formed in very specific proportions and that this ratio has been a topic of study for scientists for decades? Lithium is not only fascinating because of its scarcity, but also because of its properties. This element is known for its lightness and its ability to react chemically. Why is this important? Because those same properties make it an ideal candidate for applications in batteries, especially in the context of modern technology. So when you think about your mobile phone or an electric car, remember that lithium plays a fundamental role in their operation. As stars evolve and reach the end of their lives, something interesting happens. They begin to fuse lighter elements such as hydrogen and helium to form heavier elements. But during this process, lithium is destroyed, as if it were in a constant battle for survival. Could it be that supernovae, those bright and cataclysmic explosions at the end of a star's life, are one of the reasons why lithium is so scarce? When a star explodes, enormous amounts of energy and materials are released into space. However, lithium tends to be destroyed in this process. This raises an intriguing question. Could it be that supernovae, despite their ability to create new elements, are also responsible for the decrease of lithium in the universe? The answer seems to be yes, and that leads us to reflect on the delicate balance that exists in the creation and destruction of elements in the cosmos. But lithium is not just a mere spectator in the grand theatre of the universe. Its presence is crucial in numerous chemical processes that occur both on Earth and elsewhere in the cosmos. For example, in the formation of planets, lithium may play a role in the chemistry that enables life. This leads us to think about how such a rare element could be part of the story of life itself. Despite its scarcity, lithium is also found in unexpected places, from seawater to layers of rock on Earth. This element has managed to infiltrate various parts of our planet. How is it possible for such a rare element to be found in so many locations? The answer may lie in the fact that although lithium is rare, its ability to combine with other elements allows it to be present in chemical compounds that are more common. Now let's think about the search for lithium in other parts of the universe. Scientists use telescopes and space probes to study the chemical composition of distant stars and galaxies. What are they exactly looking for? They are searching for clues that help them understand how lithium formed in those far-off places. Through these observations, astronomers can trace the history of lithium and its evolution over time. To put it in perspective, lithium is a reminder that in the vast universe, even the rarest elements can have a significant impact. Its scarcity and its role in chemistry not only tell us the story of the formation of the universe, but also give us hints about the possibility of life on other planets. If such an uncommon element can be part of life on Earth, what other secrets might be hidden in the immensity of the cosmos? So the next time you think about lithium, remember that it is more than just a simple element. It is a fragment of cosmic history, a thread that connects the formation of stars with life on Earth. It invites us to explore and to question our place in the universe. What other mysteries await us to discover in this vast and infinite space? What is the role of stars in the creation of light elements? This is one of the most fascinating questions we can ask when exploring the vast universe. Stars, those bright points of light in the night sky, are much more than simple spheres of burning gas. They are cosmic factories where some of the most fundamental elements that make up everything we know are produced. When we think of a star, we often imagine its light and heat. But behind that brilliance lies an incredibly complex process. At the heart of each star, the conditions are extreme. The pressure and temperature are so high that they allow hydrogen nuclei to fuse together. What does this really mean? Nuclear fusion is the process that powers stars and at the same time is the reason why other light elements are created. Fusion begins with hydrogen atoms. Imagine each of them as small balls that, when joined together, form something larger. When these balls fuse, they form helium, releasing a large amount of energy in the process. This is how stars shine and provide us with light. But there is more to this story. Did you know that in the core of a star, the temperature can reach millions of degrees? That energy not only keeps the star shining, but also allows other elements to form through successive nuclear reactions. As a star progresses through its life cycle, changes occur. In the later stages, fusion continues and other elements begin to form. For example, helium can fuse to form carbon, and so on. The creation of new elements is like a cycle, where each new fusion generates something more complex. This process is fundamental to understanding how the universe has been enriched with a diversity of light elements. It is interesting to think that when we look at the stars, we are seeing not only light, but also the result of billions of nuclear interactions. Each star is a natural laboratory, where extreme conditions allow for experimentation with elements on a scale that we could never replicate on Earth. This makes the study of stars crucial for understanding where we come from and how the universe was formed. However, not all stars are the same. Some are more massive than others, and this mass determines how and when light elements are produced. Larger stars have shorter lives, but they are incredibly efficient at creating heavy elements. On the other hand, smaller stars like our Sun produce light elements more slowly and gradually. It's as if each star has its own rhythm and style of production. So, what happens when a star runs out of fuel? In the case of larger stars, the end is dramatic. Upon reaching the end of their life, they can explode in a supernova, one of the most powerful explosions in the universe. During this explosion, enormous amounts of energy are released, and in this chaos, more light and heavy elements are generated. This is a crucial moment in the history of the universe, as the expelled material disperses and becomes part of new stars, planets, and potentially life. Even smaller stars like ours have a significant impact on the creation of light elements. When a star like the Sun dies, it does not explode, but it sheds layers of gas that disperse into space. This material becomes the building block for new generations of stars. Therefore, every star we see in the sky has contributed in some way to the creation of the elements that make up the universe. It is amazing to think about how all these light elements formed in the hearts of stars are connected to our own existence. The elements that make up our bodies, such as carbon, oxygen, and nitrogen, originated in stars. In fact, it is said that we are made of stardust, a phrase that resonates deeply when we consider our connection to the cosmos. As scientists study stars and their life cycles, they also examine how these processes influence the formation of galaxies and solar systems. Stars not only create elements, but also shape the environment in which they exist. The interaction between stars, gas, and cosmic dust is fundamental to understanding the structure of the universe. Stellar nucleosynthesis is, therefore, an essential process that continues to influence the evolution of the universe. Each new element created in the heart of a star adds to the chemical diversity that makes up our world. So the next time you look up at the starry sky, remember that each star is a factory of light elements, playing a crucial role in the history of the universe and in our own existence. Stars are a reminder of the beauty and complexity of the cosmos. They teach us that although the universe is vast and sometimes bewildering, every light element we see and touch has a story to tell, a story that begins in the heart of a star. Nuclear fusion is one of the most fascinating and powerful processes in the universe. At the heart of stars, millions of tons of hydrogen exist under extreme conditions of temperature and pressure. But what really happens in such an extreme environment? Imagine a huge cosmic kitchen where hydrogen is the main ingredient and the temperature exceeds millions of degrees. In this kitchen, hydrogen atoms combine, creating helium and releasing a colossal amount of energy. This energy is what gives light and heat to our stars, and it is the reason we can see the sky shine at night. Nuclear fusion is not a simple process. A great deal of energy is required to overcome the repulsion that exists between hydrogen nuclei, which are positively charged. But how do they manage to do it? The answer lies in the extreme conditions found inside stars. The gravity of a star is so intense that it compresses hydrogen to the point where temperatures reach levels where the nuclei can get close enough to fuse. It's like having to crush a rubber ball with your hands. By applying enough pressure, it will eventually deform and join into a single block. As hydrogen nuclei fuse to form helium, energy is released in the process. This energy manifests as radiation, which radiates into space. But why is this energy so important? Without it, life as we know it could not exist. The light and heat emitted by stars are essential for maintaining the temperature of planets in their orbits, allowing water to remain in a liquid state and therefore enabling life to thrive. When thinking about the life of a star, it is crucial to understand the cycle it goes through. It begins with the fusion of hydrogen. But it doesn't end there. As hydrogen runs out, the star becomes an even hotter furnace where it begins to fuse helium into heavier elements. This chain fusion process is like a game of dominoes, where each new element created leads to the creation of another different element. Helium becomes carbon, carbon becomes oxygen, and so on until heavier elements are formed, all thanks to the incredible energy generated by nuclear fusion. But what happens when a star runs out of fuel? There comes a time when fusion stops and the star can no longer support itself against the force of gravity. At that moment, the star collapses. This collapse can trigger a massive explosion known as a supernova, which not only destroys the star but also disperses the newly created elements throughout the galaxy. This is a cycle of life and death that not only affects the star itself but also enriches the interstellar medium with new elements. which can eventually be used to form new star systems and planets. Nuclear fusion also occurs under other circumstances, such as in the case of fusion reactors that scientists are trying to develop on Earth. The idea is to replicate the process that occurs in stars to create a clean and infinite energy source. But why is it so difficult to achieve this? The answer lies in recreating the extreme conditions found in the hearts of stars. Scientists are working hard to find a way to maintain fusion in a controlled and sustainable manner, a huge challenge that could change the course of humanity. The implications of nuclear fusion are not limited to energy production. It is also a process that connects us to the cosmos. Every time we look at the starry sky, we are reminded that those bright lights are the result of nuclear fusion occurring millions of light years away, creating the elements that make us up. From the hydrogen that composes water to the carbon that forms the basis of life, we are all part of this great cosmic web. Nuclear fusion teaches us that we are made of stardust. Every atom in our bodies has gone through a cycle that began in the heart of a star. This connection to the universe reminds us how interconnected all things are. We are made of the same elements that have been forged inside stars. And in turn, those elements are part of a cycle that continues to evolve. Finally, understanding nuclear fusion is essential to comprehend not only the life of stars, but also our own existence. Every time we turn on a light, every time we feel the warmth of the sun on our skin, we are experiencing the incredible energy released by nuclear fusion. It is a reminder that, although our days may be mundane, every moment is imbued with the magic of the universe. This fascinating dance of atoms and energy continues in an eternal cycle, and we are witnesses to its effects. So the next time you look at the stars, remember that each one of them is a nuclear fusion factory, creating light elements and giving life to a constantly changing universe. Nuclear fusion is not just a cosmic process, it is part of our history and our future, a story written in the language of the stars. Supernovae are fascinating celestial phenomena that mark the end of the life of a massive star. But what happens at the moment of their explosion, and how does it affect the abundance of light elements in the universe? When considering this event, it is essential to understand that a supernova is not just an impressive visual spectacle, but a crucial process for the creation and distribution of elements in the cosmos. When a star exhausts its nuclear fuel, it can no longer sustain the internal pressure that counteracts gravity. The star collapses under its own weight, and upon reaching a critical point, it releases an unimaginable amount of energy in a fraction of a second. This explosion is not only the end of the star, but also a rebirth for many of the elements that compose it. In this chaos, extreme temperatures are generated that allow for the fusion of atomic nuclei and the creation of new elements, some of which are lighter than others. Imagine a fireworks explosion where each spark represents an element that is scattered through space. This explosion of a supernova ejects massive amounts of energy and matter into space. In fact, it is estimated that in the process, a supernova can release more energy in a few days than the sun will emit over its entire lifetime. But what are the consequences of this explosion for light elements like hydrogen and helium? Through this cataclysm, hydrogen and helium atoms are created and released into space. But not only that, other heavier elements such as carbon and oxygen are also generated, which will eventually mix with hydrogen and helium. This mixture is essential, as it is the first step in the formation of new stars and planets. We can imagine this process as a huge cosmic seedbed where elements combine and group together to form new structures. The importance of the supernova in the creation of light elements does not stop there. When the remnants of the explosion cool, they create clouds of gas and dust that eventually condense to form new generations of stars. Within these new stars, the cycle of nuclear fusion begins anew, leading to the production of more light elements. Thus, the life cycle of stars becomes a looping system where each supernova explosion not only ends a star but also gives rise to new possibilities. An intriguing aspect is how supernovae also influence the chemistry of planets. By scattering hydrogen and helium, these elements can be incorporated into the disks of material surrounding new stars. As this material condenses, planets are formed, and therefore the composition of those planets is deeply influenced by the supernovae that occurred previously. Isn't it fascinating to think that the history of a supernova can be written in the chemistry of a planet? Supernovae also have an impact on the distribution of light elements in the universe. By releasing large amounts of matter, they contribute to the mixing of intergalactic gas, allowing light elements to travel great distances and integrate into other regions of space. This means that elements that once belonged to a star may now be in a completely different galaxy. In this sense, the universe becomes a kind of vast cosmic garden where elements are continuously transported and reconfigured. However, not all supernovae are the same. There are different types, and each has a distinct effect on the production of elements. For example, type Ia supernovae are known to be richer in light elements. Why? This is because they come from stars that have accumulated matter from their nearby companions. In this case, the explosion results in an abundant release of hydrogen and helium. The relationship between supernovae and light elements is an active area of research in astrophysics. Scientists use telescopes and other instruments to observe supernovae in distant galaxies, trying to understand how they affect the evolution of the universe. Each observed supernova is like a window into the past, revealing details about the conditions of the universe at different times. In summary, supernovae are more than just spectacular explosions. They are fundamental actors in the cosmic drama of element creation. These events not only contribute to the production of light elements, but also play an essential role in the evolution of galaxies and the formation of new stellar systems. With each explosion, the universe is reconfigured, and with each star that is born, the possibility of life is renewed. Thus, in the eternal cycle of creation and destruction, supernovae remind us that we are all connected through the elements that make up our being and the cosmos we inhabit. Dark matter, although invisible and elusive, plays a fundamental role in the formation of light elements in the universe. So, what is dark matter, and why is it so important? To understand this, we must first imagine the universe as a vast ocean, where visible matter, like stars and planets, is just the surface. But just beneath that surface, there is a huge volume of matter that we cannot see. This is dark matter, which makes up about 25% of the universe. Let's think of visible matter as the ice at the top of a mountain. What we see is only a small part of what is inside. Most of the mountain, the dark matter, remains hidden, but its influence is undeniable. In fact, dark matter acts like cosmic glue, holding galaxies together and ensuring that larger structures form in the cosmos. Without this mysterious force, the universe as we know it would be a very different place. Now, how does this relate to the formation of light elements? The answer lies in gravity. Dark matter, being so abundant and having a significant gravitational influence, creates an environment where gases, primarily hydrogen and helium, can cluster together. Imagine dark matter as a large magnet in space, attracting hydrogen and helium atoms towards it, where they eventually form stars. Without this attraction, light elements would be much more dispersed, making it difficult for them to cluster and evolve into more complex structures. Gravity not only helps form stars, but also influences the temperature and pressure within them. When hydrogen and helium atoms cluster, pressure increases, and with it, temperature. This combination is crucial for initiating nuclear fusion, the process that converts hydrogen into helium and releases a tremendous amount of energy. Thus, dark matter, although unseen, becomes a key player in this cosmic theatre, allowing the right conditions for light elements to be born. But what about the creation of new light elements? As stars evolve, dark matter continues to play its role. When stars exhaust their fuel, they can explode in supernovae, releasing a large amount of energy and matter into space. This process not only disperses heavy elements, but can also generate more hydrogen and helium from the extreme conditions of the explosion. In this way, dark matter and supernovae work together to enrich the cosmos with the light elements that are fundamental for the existence of life. Furthermore, we cannot forget that dark matter also influences the formation of galaxies. By clustering visible matter and creating large-scale structures, it establishes an environment where light elements can interact and evolve. This means that dark matter is not only important for the light elements themselves, but also facilitates the necessary conditions for life to arise in different parts of the universe. The search for dark matter has led scientists to develop ingenious methods to detect it. Although we cannot see it directly, its gravitational effect on visible matter is evident. Galaxies rotate at speeds that should not be possible with only the matter we can observe. This has led to the conclusion that there must be something more, something we cannot see, but that is there. Thus, dark matter becomes a fascinating puzzle that scientists are trying to solve. The relationship between dark matter and light elements invites us to reflect on our place in the universe. While visible matter is crucial for life as we know it, dark matter acts as the backdrop that allows everything to happen. Without it, we would have no stars, no planets, and no chemistry that forms the basis of life. As technology advances, scientists are getting closer to unraveling the secrets of dark matter. What does the future hold in this quest? Perhaps we will discover that dark matter is not only an essential component of the universe, but could also contain clues about the formation of life on other planets. The exploration of light elements and their relationship with dark matter also has fascinating implications for astrobiology. By understanding how these elements formed in the universe, we can have a better idea of where to search for life on other worlds. Could there be planets where the combination of hydrogen, helium, and other light elements has led to suitable conditions for life? In summary, dark matter, although invisible, is a fundamental actor in the history of the universe. Without its influence, light elements would not have been able to form and evolve. As we continue to explore these mysteries, we move one step closer to understanding not only our own origin, but also our place in the vast cosmos. Each discovery reminds us that the universe is a complex and astonishing place full of wonders yet to be uncovered. Gravity is one of the fundamental forces of the universe and plays a crucial role in the formation of cosmic structures. Have you ever wondered how light elements like hydrogen and helium group together to give rise to stars and galaxies? The answer lies in the way gravity acts on matter in the universe. When the universe expanded after the Big Bang, it was filled with energy and subatomic particles. Over time, as the universe cooled, these particles began to come together. Gravity, which attracts everything that has mass, started to do its work. Imagine you are at a party and suddenly all the guests start forming groups. What makes some group together more than others? The answer is simple: attraction. In the same way, gravity acts on hydrogen and helium, pulling them toward each other. As gas clouds contract under their own gravity, the temperature inside them begins to rise. This process is similar to when you squeeze a rubber ball. The more you squeeze it, the more heat it generates. In the case of the universe, this compression of gas initiates a series of reactions that can culminate in the formation of stars. So what happens when the pressure and temperature are high enough? Nuclear fusion begins. Nuclear fusion is like a spark that ignites a fire. In the case of stars, that spark is hydrogen, which when fused, forms helium. This reaction not only produces light and heat, but also releases an enormous amount of energy that allows the star to shine for billions of years. Without gravity, these reactions would never have been able to start. Gravity acts like the chef who mixes the right ingredients in the kitchen of the universe. But the story doesn't end there. Gravity is also responsible for the formation of galaxies. Imagine gravity as a giant magnet that attracts dust and gas from all over the universe. As these clouds come together, they begin to spin and form more complex structures. Galaxies are like large cosmic cities where light elements group together to create stars and eventually planets. However, gravity is not only responsible for the formation of stars and galaxies, it also plays an important role in the life of these structures. As stars age, their gravity influences their evolution. Some stars at the end of their lives explode in supernovae, releasing light elements into space and enriching the interstellar medium. Gravity acts as a cycle that allows elements to be recycled, giving them new opportunities to form new stars and planets. It is fascinating to think that the same force that keeps our feet on the ground is responsible for shaping everything we see in the cosmos. How can something as simple as gravity have such a profound impact on the creation of the universe? The answer lies in its omnipresence and its ability to influence matter in ways we are just beginning to understand. In this vast universe, hydrogen and helium are the fundamental components that, thanks to gravity, become the stars that light up our nights. Without gravitational attraction, hydrogen would not have been able to group together and form the first stars. This means that gravity is not only important in the formation of structures, but is also a key player in the creation of the light elements that surround us. When you look at the night sky, each star shines as a reminder of this process. Each point of light is a story of how gravity has shaped the universe. Without this phenomenon, we would be in a very different universe. One where light elements would never have had the chance to come together and create the beauty we see today. Gravity, then, is the force that binds everything in the cosmos, from the formation of light elements to the creation of galaxies. Its influence is undeniable. This link between gravity and the creation of elements shows us that every star, every galaxy, and every planet has its origin in this powerful force. The universe, in its vastness, teaches us that there is an order behind everything. Gravity is the thread that connects all light elements, allowing them to group together and give rise to the wonders we observe in the sky. As we learn more about gravity and its role in the cosmos, we come closer to understanding not only our universe but also our place in it. So the next time you look up at the stars, remember that each one of them is a testament to the powerful force of gravity. A reminder that in the vastness of the cosmos, everything is interconnected. The story of light elements is a story of attraction, union, and transformation, and gravity is the master that guides this cosmic dance. Light elements play a fundamental role in the history of our solar system, but how did they come to be present here on Earth in the first place? To understand this, it is essential to go back in time to the moments when our solar system began to form. This happened about 4.5 billion years ago in a vast and dusty disk of gas and dust swirling around a young star, our Sun. At first, this disk was primarily composed of hydrogen and helium, the lightest and most abundant elements in the universe. But why were these elements so crucial for the formation of our solar system? Imagine that each of these elements is like a small piece of a puzzle. Without them, there simply would not be a final picture. Hydrogen in particular acted as the foundation for everything else. Without hydrogen, there would be no helium, and without helium, we would not have had the variety of elements that ultimately shaped the planets. As the Sun formed at the center, gravity began to do its work. This phenomenon, which sometimes feels like an invisible hug, attracted more and more matter toward it. But gravity did not just group hydrogen and helium around the Sun. It also helped other elements to cluster in the protoplanetary disk. In this chaotic environment, small dust particles came together, colliding and merging in a process reminiscent of a building game. Thus, little by little, the first celestial bodies began to form, the planets. The light elements did not remain only in the Sun and the planets. As Earth formed, hydrogen and helium were still present. But other elements also began to emerge. For example, water, which is vital for life as we know it, formed when hydrogen combined with oxygen. Isn't it fascinating to think that those same light elements that formed in the heart of the universe are what allow us to exist today? One of the most intriguing things about the formation of the solar system is how the light elements were distributed. At first, everything was chaos, but over time, gravity began to organize this disorder. The planets closest to the Sun, like Mercury and Venus, formed from heavier materials, while the more distant planets like Jupiter and Saturn were able to accumulate large amounts of hydrogen and helium. This process of cosmic natural selection gave each planet its own personality and composition. And what about Earth? Despite being a rocky planet, hydrogen and helium also played a crucial role in its formation. Over time, Earth cooled, allowing oceans and an atmosphere to form. This primitive atmosphere was largely composed of water vapor, a clear reminder of the importance of hydrogen in our world. Without those light elements, Earth would be a very different place, perhaps even uninhabitable. When we look at the sky today, we see shining stars, but we also see the imprint of those light elements. Stars are factories of elements, and many of them, at the end of their lives, explode in supernovae, scattering their components across the universe. Thus, the light elements that formed in the heart of the Sun and other stars have traveled through the cosmos, enriching the interplanetary medium and giving rise to new generations of stars and planets. The journey of light elements in our solar system is not just a story of how they formed, but also of how they have influenced the evolution of life. Every molecule of water we drink, every breath we take, is linked to those elements that were born in the Big Bang and grouped together to form our home. That connection to the universe is astonishing and significant. In summary, light elements are not just chemical components, they are the building blocks of our world. From the formation of Earth to the creation of water, these elements have been at the heart of every process that has shaped our planet. The story of how they got here is a testament to the beauty and complexity of the universe. As we explore more about light elements, we realize that their presence is not limited to Earth. Every corner of the cosmos is imbued with these small but powerful particles. Every star, every planet, every drop of water is a reminder that we are all connected through the history of the universe. The quest to understand how light elements were distributed in the solar system continues to be a fascinating topic for scientists and curious minds alike. Each discovery opens new pathways to understanding our place in the universe, so the next time you look at the night sky, remember that you are gazing at a vast sea of history, where light elements play a central role in the fabric of the cosmos. Water, that vital liquid that covers more than 70% of our planet, plays a fundamental role in the existence of life as we know it. But have you ever wondered where the elements that make up water come from? The answer takes us on a fascinating journey through the cosmos, specifically to the light elements, hydrogen and oxygen. To understand the chemistry of water, we first need to know its two main components. Hydrogen, the lightest and most abundant element in the universe, is like the basic building block that initiates many chemical reactions. On the other hand, oxygen, although a bit heavier, is equally essential. Together, these elements form water, which is not only crucial for living beings but also acts as a universal solvent, facilitating chemical reactions in our bodies and in the environment. Let's imagine for a moment what Earth would be like without water. An arid, dry planet without rivers or oceans where life could not thrive. Water is the medium in which many of the chemical reactions necessary for life occur, from photosynthesis in plants to digestion in animals. How did this wonderful substance form on our planet? Hydrogen was one of the first elements to appear after the Big Bang. In the early moments of the universe, hydrogen and helium were created during primordial nucleosynthesis. Over time, this hydrogen grouped together under the influence of gravity, forming giant clouds that would later become stars. And this is where the story of water becomes even more interesting. When stars are born, a process called nuclear fusion occurs within them. This process not only produces energy but also transforms hydrogen into helium and other heavier elements. At the end of their life cycle, many stars explode in supernovae, releasing elements into space, including the necessary amount of oxygen. This oxygen combines again with hydrogen, forming water in the gas clouds surrounding new stars and planets. But how did water get to Earth? During the formation of the solar system, many scientists believe that water was introduced to Earth through comets and asteroids, which are rich in ice. When these celestial bodies collided with our primitive planet, they released enormous amounts of water. Thus, Earth began to accumulate the water that we know and value so much today. Hydrogen is not only crucial for the formation of water, but also plays a vital role in the chemistry that sustains life. In our bodies, hydrogen is part of DNA molecules, proteins, and carbohydrates. Without it, we could not exist. Water, being such an abundant compound, facilitates the interaction between these vital components, allowing essential biological processes to develop. On the other hand, oxygen, which is part of water, is equally fundamental. It is the element we breathe and that plants use to perform photosynthesis, a process that produces oxygen as a byproduct. Without photosynthesis, life on Earth would be completely different, and perhaps it wouldn't exist at all. The chemistry of water also has implications for the search for life on other planets. Scientists are constantly looking for signs of water on other worlds, as the presence of water is one of the main indicators that a place could harbor life. In fact, on Mars, evidence of water has been found in the form of ice, which has sparked curiosity about the possibility of life in the past or present on that planet. But water is not only important in the context of life, it also plays a crucial role in regulating the climate and environment on Earth. It acts as a thermal regulator, helping to maintain stable temperatures that are conducive to life. Oceans, rivers, and lakes are not only sources of water, but also complete ecosystems that support an incredible diversity of life. As we delve deeper into the relationship between hydrogen, oxygen, and water, we realize that everything is interconnected. From the formation of elements in the universe to life on our planet, every part of the cosmic puzzle has a role to play. So the next time you drink a glass of water, remember that you are holding in your hands a product of millions of years of cosmic processes. Hydrogen and oxygen, forged in the hearts of stars and brought to Earth through comets, have created a liquid that is not only essential for life, but also a symbol of the connection between the universe and us. The story of water is a story of origin, creation, and cosmic interconnections. It reminds us that we are part of a vast universe where every small element has its place and purpose. The next time you contemplate the vastness of the sky, think of the water flowing around you, its powerful role in the chemistry of life, and its connection to the cosmos. What allows stars to shine and life to flourish on our planet? The answer lies in a powerful reaction that occurs at the heart of stars: nuclear fusion. This process is fundamental for the production of light elements, and understanding how it works helps us unravel the secrets of the universe. Nuclear fusion is like a grand cosmic dance where atomic nuclei come together, creating something new and releasing a tremendous amount of energy in the process. Imagine you have two small balls of modeling clay. If you combine and flatten them, you get a larger shape. In the case of fusion, hydrogen nuclei combine to form helium, and in doing so, they release energy. This energy is what makes stars shine brightly and emit light and heat. But why is hydrogen the star of this dance? The answer is simple: it is the lightest and most abundant element in the universe. This means there are many more hydrogen balls available to join together and form helium. Additionally, hydrogen nuclei are small and light, making it easier for them to come close enough to fuse. Thus, in the core of a star, hydrogen is converted into helium through multiple fusion reactions that occur in a harmonious and continuous dance. As a star consumes its hydrogen, it begins to deplete this resource. But don't worry, this doesn't mean the party is over immediately. Once hydrogen is converted into helium, the conditions in the star's core change. Temperature and pressure increase, allowing helium to also fuse into heavier elements like carbon and oxygen in a similar process. This fusion cycle is what fuels stars throughout their lives. However, stars are not eternal. When a star exhausts its fuel, its life comes to a dramatic end. But at this point, nuclear fusion has left a legacy. Supernova explosions, for example, are the result of these final blasts and are capable of scattering the newly formed elements throughout space. This is how light elements such as hydrogen, helium, and others spread across the universe, enriching the interstellar medium and providing the raw materials for new stars and planets. Nuclear fusion also has implications for the search for energy on our planet. Scientists have been trying to replicate this process on Earth to develop a clean and virtually inexhaustible energy source. The idea is that if we can contain fusion in a controlled environment, we could harness the same energy that powers the stars. It is a monumental challenge, but the reward could be enormous. When observing the night sky, each star we see is a reminder of this nuclear fusion process. Each bright point is not only a beacon in the darkness, but also a testament to the incredible energy released when nuclei fuse. Each star tells a story of formation and transformation, connecting us to the vast universe we inhabit. The fusion process not only creates energy, but also influences the chemistry of the universe. As new elements are formed through fusion in stars, they combine and create complex molecules that can eventually give rise to life. It is fascinating to think that the very elements that make up our bodies and our planet were forged in the interiors of stars that have existed for millions of years. Moreover, nuclear fusion also plays a crucial role in the evolution of galaxies. The stars that are born, live and die within these immense cosmic structures not only generate energy, but also scatter elements that become part of new stars, planets, and ultimately life. Through this endless cycle of creation and destruction, nuclear fusion acts as a driving force of the cosmos. Fusion energy is not limited to being just an astronomical phenomenon. It is also a powerful reminder of the interconnectedness of all elements in the universe. Every atom that makes up our being has a story to tell, a story that begins in the heart of a star. So the next time you look up at the sky, remember that you are seeing not just light, but also the traces of nuclear fusion that shape our world. Understanding nuclear fusion and its role in the creation of light elements illuminates not only our cosmic history, but also our future. As we advance in scientific research, the search for energy, and the exploration of the universe, there will always be a common thread that unites us: the fusion energy that shines in every star and in every corner of the cosmos. What happens when a star reaches the end of its life? This is a fascinating question that leads us to understand the stellar life cycle and its impact on the creation of new elements. Stars, those bright giants that illuminate our night sky, are not just celestial bodies. They are cosmic factories that produce elements through complex nuclear fusion processes. As a star consumes its fuel, it transforms and, in the end, explodes in an impressive event known as a supernova. But how exactly do stars contribute to the formation of light elements? It all begins in the heart of a star, where the temperature and pressure are so intense that hydrogen nuclei combine to form helium. This process, called fusion, is what allows stars to shine and emit energy. But the story doesn't end there. As stars evolve, they move on to more advanced phases of fusion, creating heavier elements from lighter ones. For example, in the largest stars, helium can fuse to form carbon, oxygen, and other essential elements. In this way, stars act as true cosmic forges, converting hydrogen into elements that are fundamental to life as we know it. However, what happens when a star exhausts its nuclear fuel? As it reaches the end of its life, the star undergoes dramatic changes. If it is massive enough, it can explode in a supernova, scattering a mix of newly formed elements into space. Imagine throwing a handful of sand into the wind. The grains scatter everywhere, and the same principle occurs with the elements generated in a star's explosion. This process is not only spectacular but also vital. Supernovae enrich the interstellar medium with new elements, which can then be used by other forming stars, planets, and eventually life itself. The importance of these events cannot be underestimated. Every time a star explodes, it is sowing the universe with the necessary ingredients for the creation of new stars and planets. Without supernovae, many of the light elements we consider essential, such as carbon and oxygen, would not exist in the abundance they have today. Thus, the death of a star becomes the life of other cosmic entities. Now, how does all this relate to the light elements we have mentioned? The answer lies in the production chain. While hydrogen and helium were created in the early moments of the universe, the heavier elements generated in stars, such as carbon and oxygen, begin to become part of the fabric of life. These elements are fundamental for the formation of complex molecules. such as DNA and proteins, which means that, in a sense, we are made of the ashes of stars that lived and died billions of years ago. The life cycle of stars offers us a unique perspective on our own existence. Is it possible that every time we look at the starry sky, we are seeing the stories of those stars that have given their lives for us? This connection is not only poetic, but also reminds us of how intricate and interconnected the universe is. Every star, every explosion, every light element is part of a great cycle that has shaped the matter that composes our planet and our own being. Throughout history, scientists have sought to understand this process. Modern astrophysics studies the remnants of supernovae and interstellar gas to learn more about stellar evolution and the distribution of elements in the universe. This is not just out of curiosity, it has practical implications. Understanding how elements form in the universe can help us decipher the origin of life on Earth and potentially elsewhere. The evolution of stars also raises intriguing questions about the future of the universe. Over time, stars will continue to be born and die, and the cycle of element formation will continue. But what will happen when the last stars go out? Could the universe become an empty place, devoid of the light of stars? These questions invite us to reflect on the fate of our existence and the role we play in this vast cosmos. So every time you think about the universe, remember that we are part of a story that began billions of years ago. Every light element in our body, every molecule of water we drink, has its origin in the stars. The evolution of stars is not just an astronomical phenomenon, it is a narrative that connects our lives with the fabric of the cosmos. Ultimately, by understanding the life and death of stars, we are getting closer to understanding our own place in the universe, in a journey that we have only just begun to explore. What do the water you drink, the air you breathe, and the living beings that inhabit the earth have in common? The answer lies in the light elements. These elements, such as hydrogen and helium, are the fundamental building blocks of matter on our planet. But how did they come to be here? The story of light elements on Earth is fascinating and provides us with a unique perspective on our own existence. Hydrogen, the simplest and most abundant element in the universe, accounts for approximately 75% of visible matter. Imagine the universe as a giant puzzle, with hydrogen being the largest piece. Without this element, life as we know it would not be possible. But what role does hydrogen play on Earth? It is the main component of water, which is essential for life. Without water, ecosystems, plants and animals as we know them would not exist. Now, helium, although not as abundant as hydrogen, also has its importance. This element, often associated with party balloons, is a product of nuclear fusion in stars and has accumulated on our planet over billions of years. Helium is a noble gas, meaning it does not easily react with other elements. This makes it an essential component in certain industrial processes, but its presence on Earth also leads us to reflect on the history of the universe. The scarcity of lithium, another light element, is particularly intriguing. Although it is less common than hydrogen and helium, lithium is fundamental in the manufacture of batteries and other electronic devices. So why don't we find as much lithium on Earth? This is because most of the lithium in the universe was formed during primordial nucleosynthesis, but its production in stars and supernovae is limited, making it rare compared to other elements. Light elements are not only important for our daily lives, but they are also crucial for understanding the geological history of our planet. As Earth formed from the accumulation of dust and gas in space, these elements grouped together to give rise to essential chemical compounds. Have you ever wondered how the chemistry of hydrogen and oxygen combines to form water? This combination is one of the most important reactions that enables life. Furthermore, the role of gravity in the formation of light elements cannot be underestimated. Gravity acts like a magnet, pulling hydrogen and helium toward the center of forming stars. As these elements cluster together, they generate extreme temperatures and pressures that allow nuclear fusion to occur. This process not only provides light and heat to stars, but also creates new elements from the light ones in their cores. Let's talk about how light elements are distributed on Earth. The atmosphere, water, oceans, and soil are largely composed of these elements. For example, hydrogen is the main component of water, while helium is present in small amounts in the atmosphere. However, lithium is much rarer and is found in specific minerals. This leads us to wonder, how have these elements been distributed over time? Geological processes such as volcanic activity and erosion have played a crucial role in redistributing these elements. Imagine a huge cycle in which hydrogen and oxygen combine to form water, which then evaporates, condenses, and returns to Earth as rain. This constant cycle is fundamental to life and ensures that light elements are always in motion. As we explore the composition of Earth, we also discover that light elements are essential for the chemistry of life. Carbon, oxygen, and nitrogen, although not light elements in the strictest sense, combine with hydrogen to form organic compounds. These combinations are the basis of biological molecules such as DNA and proteins, which are fundamental to all living beings. The presence of light elements on Earth also has implications for the search for life on other planets. If scientists are looking for signs of life on Mars or on the moons of Jupiter and Saturn, one of the key factors they consider is the availability of water and, therefore, hydrogen. The existence of these elements is an indicator that there could be suitable conditions for life, even in places that seem inhospitable at first glance. In fact, light elements are so vital that their study is not limited to Earth. Astrophysicists are constantly investigating how these elements are distributed in other celestial bodies. For example, by observing the chemical composition of stars and galaxies, scientists can learn more about the history of the universe and how the elements that constitute our lives were formed. The relationship between light elements and life on Earth is a reminder that everything in the universe is interconnected, from the explosion of stars that release elements into space to the formation of planets and the emergence of life. Each step in this cosmic story is crucial. Ultimately, the search and study of light elements not only help us understand our place in the universe, but also teach us about the fragility and interdependence of life itself. So the next time you look up at the sky and wonder about the vast universe around us, remember that light elements, though small, are essential for everything we know and love. Without them, Earth would not be the vibrant home it is today. In every drop of water, in every breath you take, the echoes of the universe's creation resonate, reminding us that we are part of something much larger. The search for light elements in the universe is like a great cosmic puzzle that scientists are trying to solve. When we look at the starry sky, we are not just seeing bright lights, but also clues about the composition of the universe. How do we know what elements are present on a distant planet or in a faraway star? The answer lies in the light they emit. Light is not just a visual phenomenon, it is a powerful tool. When the light from a star passes through its atmosphere, it interacts with the elements present and leaves a unique fingerprint. It's as if each element holds a secret in the form of light patterns. Thus, astronomers use spectroscopes to analyze this light, breaking it down into its component colors like a rainbow. But what lies behind this fascinating technique? Each element has a specific set of spectral lines which are like its signature. For example, hydrogen has a set of lines that make it identifiable, just as each person has unique fingerprints. Scientists can compare these signatures with those obtained from stars and other celestial bodies, allowing them to deduce which elements are present. In this way, light becomes a messenger that tells us stories about matter in the cosmos. But what happens if we want to search for light elements in a specific place, like a moon or a planet? This is where space missions come into play. The probes and rovers we send into space are equipped with instruments designed to analyze the surface and atmosphere of other worlds. These tools can perform on-site chemical analyses and gather real-time data. Imagine having a small laboratory on another planet. That is exactly what these missions do. One of the most emblematic examples is the mission of the rovers on Mars. These exploratory vehicles have been collecting samples of Martian rocks and soil, searching for signs of water and light elements. The importance of hydrogen and oxygen in the search for life makes their detection crucial. Isn't Mars the planet where signs of liquid water have been found in the past? Undoubtedly, light elements could offer clues about the possibility of life. The search is not limited to our solar system. Space telescopes such as the Hubble Space Telescope or the new James Webb are exploring distant galaxies. These telescopes can observe how the light from distant stars shifts and changes as it travels through space. This phenomenon, known as redshift, allows scientists to understand how light elements are forming and evolving in the universe over time. Astrophysics also plays an important role in this search. Researchers can simulate conditions of different cosmic environments in laboratories on Earth. This allows them to understand how light elements behave under various circumstances, replicating what might happen in stars or in intergalactic space. Isn't it amazing to think that through experiments in a laboratory we can unravel the secrets of the cosmos? Meteorite studies are also an invaluable source of information. When meteorites fall to Earth, they bring us fragments from other worlds. By analyzing their composition, scientists can obtain data about the light elements that existed in the primordial solar system. These small space travelers tell stories that help us understand how the elements that make up our own planet were formed. Delving into chemistry, scientists also use mass spectrometry techniques. This method allows them to measure the abundance of isotopes of different elements, providing information about their origin and evolution. For example, by studying helium in meteorites, scientists can infer how it formed in the universe and its relationship with hydrogen. But what about light elements on other planets? Observations of exoplanets, those that orbit stars outside our solar system, have revealed that many of them have atmospheres containing light elements. This opens the door to new questions. Could they harbor life? What conditions allow the existence of these elements on other worlds? The search for light elements also leads us to consider the future. With advances in technology, we are developing new ways to explore the cosmos. Projects like the Next Generation Space Telescope promise to take our understanding of light elements to a new level, allowing for more detailed observations of planets and stars. Human curiosity knows no bounds, and each discovery brings us one step closer to unraveling the mysteries of the universe. In summary, the search for light elements is a fascinating journey that combines light, chemistry, and space exploration. It allows us to understand not only our own existence, but also that of other worlds in the vast universe. Each star, each planet, and each meteorite we analyze gives us a new piece of the cosmic puzzle. So, the next time you look at the sky, remember that there is much more than meets the eye. The stories of light elements continue, and we are just at the beginning of this wonderful journey. Did you know that light elements are fundamental to understanding life in the universe? From the hydrogen that makes up most of the matter around us to the oxygen we breathe, light elements are the building blocks of everything we know. But what role do they play in the search for extraterrestrial life? The connection between light elements and astrobiology is deeper than it seems. To begin with, let's talk about hydrogen. This element, the simplest and most abundant in the universe, is like the basic brick of construction. If we think of life as a great city, hydrogen would be the building material used in almost all structures. But why is it so crucial in the search for life on other planets? The answer lies in its ability to form compounds. When hydrogen combines with other elements like oxygen, it creates essential molecules for life, such as water. Without water, there is no life as we know it. So in the search for habitable planets, scientists look for the presence of hydrogen and therefore water. Helium, while not as reactive, also plays an interesting role in this story. One might think of helium as the quiet neighbor in our city of life, not participating much in chemical reactions but present in large quantities in the universe. Its presence indicates that at least at some point there was a good amount of hydrogen that fused in stars. But what does this mean for astrobiology? If we find helium, we could infer that somewhere nearby there were stars that produced hydrogen, which may indicate that conditions for life existed in the past. Now let's talk about lithium, an element that is a bit rarer compared to hydrogen and helium. It is often given less importance, but its scarcity is what makes it interesting. In astrobiology, the search for lithium can provide clues about a planet's chemical history. The presence of lithium may indicate unique stellar formation processes or interactions with other elements. In other words, it could be an indication that a planet has had a rich chemical history, which could present opportunities for life. But how do scientists search for these elements on other planets? One of the most powerful tools in this search is spectroscopy. Can you imagine a prism that breaks light into different colors? That's how scientists work. By observing the light emanating from a planet, they can break it down and see what elements are present. Each element has a unique fingerprint in the light spectrum, allowing them to identify the chemical composition of an atmosphere. If they manage to detect hydrogen and oxygen in the atmosphere of an exoplanet, they get excited, as this could mean there is water and therefore potential for life. However, it's not just about finding water. It's also crucial to understand the context. For example, where is the planet located? Is it in the habitable zone of its star where temperatures allow for the existence of liquid water? The combination of these factors is what makes a planet a viable candidate for hosting life. So, while hydrogen and helium may be abundant in the universe, the search for suitable conditions is what really matters. As we advance in our understanding of the universe, scientists are also exploring how dark matter might influence the formation of light elements. Although we cannot see dark matter, we know it's there because it affects the gravity of galaxies. Some researchers suggest that dark matter could be related to the formation of hydrogen and helium in the early universe. This opens up a range of intriguing questions. How does dark matter affect the chemistry of planets? Could it help create more favorable environments for life? Gravity also plays a fundamental role in this puzzle. Imagine you are in a park and see how gravity makes leaves fall to the ground. Similarly, in the cosmos, gravity is constantly grouping hydrogen and helium to form stars and galaxies. These groupings are crucial because within them, nuclear fusion reactions occur that create new elements. Therefore, by studying light elements, we are not only looking into the past, but also opening a window to the future. What other elements could form inside stars? What new chemical combinations could arise on other planets? Each discovery brings us one step closer to understanding whether life, as we know it, is a common phenomenon in the universe. As scientists continue their search, each new finding about light elements provides more information about the potential for life on other worlds. Astrobiology becomes a complex web of questions and investigations where each molecule tells a story about the universe, and in this search, light elements are the keys that can help us decipher the enigma of life. So the next time you look at the starry sky, remember that the stars are not just bright lights, but also factories of elements that can give life. The search for those light elements is an adventure that has just begun, and each new discovery could be the first step toward answering one of humanity's oldest questions: are we alone in the universe? The vastness of the universe is astonishing, and in its immensity, light elements play a fundamental role, like the foundations of a house under construction. Without them, not only would our planet not exist, but we also wouldn't have life as we know it. Have you ever wondered what the connection is between the hydrogen we breathe and the stars that shine in the sky? The answer to this question is key to understanding how everything around us has formed. Light elements such as hydrogen, helium, and lithium are not only the building blocks of the universe, but they also witness a story that begins billions of years ago at the moment of the Big Bang. This extraordinary event, which marked the beginning of time and space, is where everything started. Without the primordial explosion, the universe would not have had the opportunity to expand and cool enough to allow the formation of these essential elements. Primordial nucleosynthesis was the first chapter of this cosmic story. In those initial moments, the nuclei of hydrogen, helium, and lithium were forged from the first protons and neutrons. This process is comparable to how a chef combines ingredients to create a delicious dish. Without those basic ingredients, we couldn't enjoy the diversity that cooking has to offer. Thus, these light elements became the ingredients for future life. As the universe expanded and cooled, it entered the era of radiation. Imagine an oven that is slowly cooling down. As the temperature decreases, it becomes possible to cook something new. In this case, the temperature and density of the universe allowed hydrogen and helium nuclei to combine, creating an environment conducive to star formation. Without hydrogen, helium could not have been created, and without helium, it would have been impossible to form more complex elements. The importance of hydrogen cannot be underestimated. It is the most abundant element in the universe, and one could say it is the foundation of everything. Why is it so crucial? Because it is the main actor in nuclear fusion within stars, where it transforms into helium and releases energy in the form of light and heat. This process not only illuminates the cosmos, but also allows planets and therefore life to flourish. Helium, another protagonist in our story, was formed from the fusion of hydrogen in the hearts of stars. It is a light element that, despite its simplicity, has an enormously complex role in the structure of the universe. It is often considered a residual element compared to hydrogen, but its presence is fundamental to understanding the evolution of stars and, ultimately, the composition of entire galaxies. On the other hand, lithium is an interesting case. Despite being a light element, its quantity in the universe is surprisingly scarce. The creation of lithium is linked to specific processes that occurred in the early universe, and its scarcity reminds us that not all elements are created equal. Imagine a market where some products are abundant and others are hard to come by. That is how the universe is in terms of light elements. Stars are not only factories of energy, they are also responsible for stellar nucleosynthesis. Throughout their life cycle, stars create new elements from the fusion of light ones. When a star reaches the end of its life, it can explode in a supernova, scattering these elements into space and enriching the interstellar medium. It is an endless cycle of creation and destruction, where each explosion carries with it the promise of new worlds and new forms of life. When observing the universe, it is essential to recognize the relationship between dark matter and light elements. Although dark matter cannot be seen, its influence is undeniable. It acts as a skeleton that supports the structure of the universe, helping to group hydrogen and helium to form stars and galaxies. Without this mysterious matter, the universe would be a very different place, and the formation of light elements would be a challenge. Gravity plays an equally crucial role in this cosmic dance. Imagine a great attraction that binds light elements together, allowing them to cluster and form stars. As gravity becomes stronger, hydrogen and helium atoms come together, forming the stars we see in the sky. Without this powerful force, the universe would be a chaotic place where nothing could unite to create the beauty we appreciate today. As we explore our own solar system, we find that light elements are everywhere. From planets to comets, these elements have been present in the formation of our cosmic home. The chemistry of water, which is essential for life, is a clear example of how hydrogen and oxygen combine to create something fundamental. Without hydrogen, we wouldn't have water, and without water, life as we know it would be impossible. The energy of fusion, which is produced from the union of light elements, is the force that drives stars. This process not only generates light and heat, but is also the source of energy that allows stars to shine for millions of years. The evolution of stars from their birth to their death is an impressive journey that leads to the creation of new elements, vital for the existence of life. On Earth, light elements have a profound impact on our daily lives and the environment around us. From the hydrogen in the water we drink to the oxygen we breathe, these elements are an integral part of our existence. Without them, not only would the elements that form our bodies be missing, but the biodiversity that makes our planet a special place would also be lost. Finally, the search for light elements in the universe is a fascinating field of study for scientists. Using telescopes and other tools, researchers explore the depths of the cosmos, trying to identify these elements in other galaxies and planets. This search not only helps us understand our place in the universe, but also raises intriguing questions about the possibility of life on other worlds. Understanding light elements is essential for astrobiology, as it provides us with clues about how life has developed on other planets. Could these elements be the key to finding life on distant worlds? The answer to this question could change our perception of what it means to be alive in the cosmos. At the end of this journey through the history of the universe, it is evident that light elements are much more than simple components of matter. They are the protagonists of a cosmic narrative that spans billions of years. By understanding their importance, we not only get closer to the essence of the universe, but also celebrate the wonderful complexity of life itself.